Now, on our previous video, we looked at operators and how they are actually extracting various observables from an eigenfunction. So we're going to build on that and look at theorem of separability. And in this particular topic, we'll dive specifically first into looking at a two-dimensional case, and this is going to be important because by so doing, we'll be able to separate various variables that may affect a particular molecule or a property or particle in a quantum realm. So in here, looking at in two-dimensional case, we have a situation where looking at the Hamiltonian operator is acting on a particular wave function which is actually two-dimensional. In this case, this is actually equal to the energy total or the solution energy, and this solution energy spits out the same function. Now this particular wave function is kind of like an eigenfunction, and in this particular solution, which is the energy total, this is actually the eigenvalue. So the eigenvalue is not an operator, but it's actually related more to the operator, which is a Hamiltonian operator in the Schrödinger's equation. Now in this part, what we recognize is that we need to be able to put our Hamiltonian operator into two variables, which are the x and the y variables. So in this case, for Hamiltonian, what we get is where our Hamiltonian operator is actually equal to the sum of the Hamiltonian on the x coordinate plus that of the y coordinate. And in this particular case also, we're just going to make this to be a, and in this particular case as well, we need to look at how we can separate or evaluate our wave function in this case. So for our wave function, which brings our x variable and y variable together, to actually separate them, what we do is that we multiply our wave function on the x coordinate, the wave function on the y coordinate, and this is actually term number b. And finally, our total energy, which is, I would say, the solution, this is actually equal to the sum of the energy on the x plus that on the y. This is actually represented as c. So what we recognize in here is that making this to be number one, I'll just put it in that particular sense. What we recognize in this particular three is that we actually can separate our Hamiltonian operator or the Schrödinger equation into two variables. The first variable in here, which is the x, shows that our Hamiltonian on the x coordinate is actually acting on our wave function on the x coordinate, and this is equal to the energy on the x coordinate and spitting out the same wave function on the x coordinate. And on the other side, on our y, we have the same thing happening in there, and it's kind of interesting to see how we can actually move ahead from this into how we can actually bring those together to actually not only target specific coordinates independently, or I would say variables independently, but bringing them together. So looking at this, so to get to this particular point, what we need now to do is to substitute R, A, B, and C in equation 1 in order for we to be able to bring all these coordinates together and actually solve them independently. So as a result of that, what we have is the sum of the Hamiltonian operators is acting on the individual coordinates, and take note that they are actually independent in here, so you can't or you cannot in the play act x on y. However, you only have to act on the x alone and also act on the y's alone in order for we to get the coordinates on those specific variables independently. And this can also be expressed as just RH, which is a Hamiltonian operator, and this is equal to eigenvalue, which is the energy. So this is about it for actually introducing the theorem of separability and how this can actually be important in actually targeting specific variables that can actually affect a particle in any coordinate, either in 2 dimensions, or you can actually build on this in 3 dimensions in terms of the Hamiltonian operator or any operators in quantum theory. So a specific example in here is going to be looking at, let's just say, a particular diatomic molecule, which is hydrogen chloride, and in here we have the chlorine here, and we have the hydrogen in there, and we have the bond in here. And what we see is that since this is a 2-body problem, this can be reduced in here into a 1-body problem. And in this particular case, for we to reduce it from a 2-body problem to a 1-body problem, what we need to do is to make assumptions by actually saying that our vibrational motion is actually independent of our translational motion of the center mass. So in this case here, our center mass will be expressed as xcm, and for our vibrational motion, our coordinate for this will be just small letter x. So in this particular case, what we can now do in here is actually introduce our Hamiltonian operator for this. So our Hamiltonian operator for this actually shows that for our translational motion operator, it's actually expressed as this, with our center of mass, where m1 is actually the mass of chlorine and m2 is the mass of hydrogen, and this is actually the second partial derivative with respect to the center of mass square of this particular molecule. While on the other side, we're going to look at this added to our vibrational motion Hamiltonian operator, and what we get is the Planck constant squared divided by 2 mu, and this is actually multiplied by the second derivative partial with respect to x squared, and this is added to, I would say, our constant r squared, which is more of the first constant right there. So once we have this, which is a huge representation of our translational motion, and this to be a huge representation of our vibrational motion that affects this R diatomic molecule, take note that this must be independent of each other. So once it's independent of each other, then you can actually separate them and act on them individually, and thereby resulting in our final values, which will be in terms of the Hamiltonian operator, in terms of the translational motion, which is what we have right here, coordinates, and on the other side we have our vibrational motion right here for the Hamiltonian operator. So take note that these operators will actually act on their own respective wave function, where the wave function is actually expressed as this. Wave function total tie is acting on the translational motion coordinate and that of the vibrational coordinate, and this is actually equal to a multiplied by exponent to the power of plus both I square root, it's going to be a long square root, to m1 plus m2 all multiplied by the energy center of mass, and this here is all multiplied here by the translation motion center of mass, which is with respect to x, and while this is going to be divided by the Planck constant, and this is all multiplied here by this other segment, which is more of a representation of the vibrational aspect, alpha divided by pi all the way to the fourth root, all multiplied by e, the exponent, to the power of alpha divided by 2. So you have to take note in here that this particular part, which is the green here, is actually more of a free particle ground state in terms of the translational motion, and while the red part here is a harmonic oscillator, where we're looking at the ground state in this case, where x is, or our wave function here is 0, while on this side here the wave function for this, make this green, to be plus or minus, because in here we're looking at the translational motion, so you're going plus or minus in that particular case. But in terms of the harmonic oscillator, we're looking at energy levels going from the ground state to the first state, second state, and end to infinity. So that's about it for this particular video. Please hit a comment down below, let me hear your thoughts about this and many more. By that way, I can talk to you all later. Stay smart and believe in yourself.